Okay, class, this is part 2 of periodicity. We are going to finish the unit on atomic theory and periodicity today. Objectives: we will be able to explain the effect of increasing nuclear charge on the radial density function in many electron atoms. Okay, we will explain the variations in bonding atomic radii among the elements and predict the relative sizes of atoms based on their position on the periodic table. We will also explain the observed changes in values of the successive ionization energies for a given atom. Your homework: you need to complete Quest Quantum Concept 8C. You should have done Quest 8A, Quest 8B, and Quest 8C. You want to finish with all your quests, and including Quest Periodicity. There's a fourth one, Quest Periodicity. Complete it so you can have time for your labs. Okay, this is the most important term you will be using to explain any trend they ask you for the rest of the unit. Alright? Effective nuclear charge. Listen carefully. Effective nuclear charge. The symbol we are using is Z subscript EFF. Okay? You will hear sometimes people say ZEF. What exactly it is? Effective nuclear charge is a measure of the attractive force between the nucleus and the valence electrons. The inner shell electrons act as insulator. Whenever you will be explaining the trend in atomic radius, in ionization energy, in electron affinity, in electronegativity, going across a period, I need for you to use effective nuclear charge as an argument to explain those trends. Effective nuclear charge is the force of attraction between the nucleus and those valence electrons. What do they really feel? The formula to find effective nuclear charge is Z minus the electrons in the inner shells. What does that mean? Effective nuclear charge equal your Z is the number of protons. Z is the atomic number. Atomic number. That means number of protons minus the core electrons or inner core electrons or all the electrons that are not valence electrons. When you do that subtraction, to make it easy for you, it will really end up being the group number. Okay, for the A's, the group number. So if I, for example, if I'm looking for the effective nuclear charge in carbon, I use the number of protons of carbon minus the core electrons, the electrons that are not the valence electrons. That effective nuclear charge should give me 4. The group number will give you the effective nuclear charge. The higher the effective nuclear charge, the more force of attraction toward the nucleus, and you will see how it affects the rest of the properties. So this is periodic trends in atomic properties. Okay? Atomic size, atomic radii, different term you will be using. The attractive forces dissipate with increased distance. The farther those electrons are from the nucleus, the larger the atom will be. That means less attraction toward the nucleus. Remember last year I talked about the babysitter being those protons, those positive figure in the atom, and you have those energetic kids that are the valence electrons running around. So the more babysitter you have in the center of the atom, the more attraction they will have to those energetic kids, the closer those energetic kids will be to the babysitter. So the trend in atomic radius decreases as you go from left to right in the periodic table. Let me tell you, students always think they answer on essay right when they don't get any point at all. Remember when you say because atomic radii decreases from left to right, this is not an explanation. This is just an observation. This is a trend that you need to use an argument to explain why that trend is the way it is. You start your essay by saying, yes, atomic radius decreases as you move from left to right because. You need to add a because. That trend is not a because. That trend is an observation because of something. That something, I said, when you go from left to right, always use an argument with the effective nuclear charge. Okay? For example, lithium and beryllium. Beryllium is smaller than lithium because the effective nuclear charge in beryllium is 2, which is greater than effective nuclear charge of 1. That means there is more attractive forces toward the nucleus of the atom. That means it's getting smaller. Okay? More attractive force. Let me repeat for the 3rd time. To explain a trend from left to right, use effective nuclear charge as an argument. Now let's go down. The trend in atomic radius. Atomic radius increases as you go down a group. You do not use effective nuclear charge for that argument. This is what you use. You use energy levels. Okay? As you go, why does it increase as you go from top to bottom? Because as you move from top to bottom, the number of energy levels increases. Lithium has 2 energy levels, 2 rings, 2 shells. Okay? Sodium has 3, potassium has 4. So if you have more energy levels, more principal quantum numbers, if you have more shells, of course those valence electrons will be farther away from the nucleus. So talk about distance from the nucleus going down a group. Talk about nuclear charges going from across a period as argument. Alright? Next. So I don't think I'm going to take time to do all the practices. So if you are watching the video, you stop it right now, you can practice. But let me quickly tell you, for cations, because cations, they are losing electrons, a cation is smaller than the parent atom because you lose electrons. In other words, for example, if I have beryllium Be2 plus and I have Be2 plus is smaller because it lost those last electrons in that last shell. Okay, Be is larger than Be2 plus. For an anion is larger than the original atom because you are adding electrons to that neutral atom. So more electrons, electron repulsion, more electrons in that shell. So it will be larger. So if you are finding the trend in a series of cations, you can use the same trend as a series of those neutral atoms. But remember, comparing a cation to the neutral atom, cation is smaller. Comparing an anion with a neutral atom, the anion is larger, more electrons. Next, what are ionization energy? Review from last year is the energy required to remove the most loosely held electron from an atom in the gaseous state. If you don't put in the gaseous state, you may not get credit, because they want to compare all the elements in the same state. It wouldn't be fair to compare sodium as a solid to see how much energy you can use to remove an electron with fluorine as a gas. It wouldn't be fair. So you put all the elements in the same state, and then you compare the energy. When it said the most loosely held electron, what it really means, it is for first ionization energy. The first ionization energy is the energy required to remove the most loosely held electron from an atom in the gaseous state. The second ionization energy is the energy needed to remove the second element from the cation, not from the neutral atom. You already removed the first one, you have a cation. Now you are removing an electron from that cation. And I will tell you that the second ionization energy is always greater than the first one. The second one. The third one will be greater than the second one, because you are removing it from a cation. The farther the electron from the nucleus, the easier it is to remove it. I need for you to think of those energetic kids. The farther they get from those positive babysitter, the easier it is for that kidnapper to come and get them. Okay? Alright, so the farther those electrons, the easier. The lower is the ionization energy. Let me see if I miss anything. Now, you should be able to explain the trend in ionization energy. You learned first year, ionization energy increases from left to right across a period. Remember, this is not an explanation. You need to use effective nuclear charge, because as you move from left to right, the effective nuclear charge increases. Therefore, the force of attraction toward the nucleus increases. Therefore, it becomes harder to remove those electrons. Therefore, you need more energy, higher energy. Ionization energy decreases as you go down a group, because as you go down a group, those valence electrons are farther away from the nucleus. Therefore, it's easier to remove them. They are less tightly held by the nucleus, easier to remove them, less energy. You need to use a good argument to get credit. And let me tell you, it does not mean to write a lot. Anyone who writes more than 3 sentences to explain this, believe me, you are just trying to see if the teacher can find something in those sentences to give you 1 point. If you are a very good writer, any of those arguments should be done in 1 or 2 sentences. And if you are not really that good at explaining, no more than 3 should do it. No more than 3. Okay, now it says, why is the ionization energy of oxygen lower than that of nitrogen? Very important AP question. Now, you learned the trend in first year. The thing with AP, they ask you questions on the exceptions. Let me show you what happened, and I promise you, you will have this on your unit test, and you should have it on the AP exam also. Listen carefully. Why is the trend in ionization energy of oxygen? This is oxygen. I need for you to look at the periodic table. Lower than that of nitrogen. It does not make any sense. I thought we said ionization energy increases from left to right. Look at nitrogen. Oxygen is to the right. Normally, oxygen should have a higher ionization energy, but this is not what happened. Oxygen has a lower ionization energy. You need to start by stating the rule. As you move from left to right, effective nuclear charge increases. It should have a higher ionization energy, but it is an exception. I would strongly advise you to explain all those exceptions, to use either electron configuration or orbital notation to show what you are talking about. So I'm going to use orbital notation for the valence electrons of oxygen and nitrogen. Nitrogen is 2s2, 2p3. This is nitrogen. 2s2, 2p. 1, 2, 3. 2p3. This is nitrogen. Here is oxygen. It is 2s2, 2s. This is 2. This is 2p, but it is 2p4. Listen carefully for the argument. Even though oxygen has a higher effective nuclear charge, but you are adding a second electron on that orbital, the first pairing, always use that expression, the first pairing create an electron repulsion that is greater than the attractive force from the effective nuclear charge. Let me repeat. Even though oxygen has a higher effective nuclear charge than nitrogen, but because of that first pairing, you just pair one electron, and it's not any pairing, it's the first pairing. Those electrons, both of them, remember they are negative. They are repelling each other. The first pairing on that orbital create an electron repulsion. So it is easier to remove that electron. That electron doesn't want to be there. Okay? It is easier. This is what you use for argument. Electron repulsion due to that first pairing. Remember those terms. Why is the ionization energy of aluminum? Here's another argument. Aluminum lower than that of magnesium. Let me clear this. Okay, this is aluminum. Where is it? Right here. This is magnesium. Look at the periodic table. Aluminum is to the right of magnesium. Aluminum has a higher effective nuclear charge than magnesium. Why is it then it is easier to remove that first electron from aluminum? Remember, use electron configuration or orbital notation to start, but it is not enough. Use 1 or 2 sentences to explain. Okay? Start with that observation. So if I'm writing the electron configuration for magnesium, let's go with 3s2 or orbital notation. I can use either one. 3s2, this is magnesium. But I need for you to look at aluminum. Aluminum is 3s2. This is 3p. Okay, all of them are 3p's, 3p1. Do not use energy level because both of them are in the same level. Do not use distance because it's the same main energy level. If you're not going up and down, do not use distance or main energy level. This is what you use. Even though aluminum has a higher effective nuclear charge, in both atoms, the valence electrons are on the 3rd level. But that 3p is at a higher energy state than the 3s. Okay? 3p. P are a higher energy state than S. D are higher energy state than P or S. F higher energy state than D, P, S. So what you use as argument, remember you start with what they have in common. Both of them are on the 3rd level. Okay? Even though aluminum has a higher effective nuclear charge, but that valence electron is at a higher energy state. It is easier to remove it. Alright? Let's see. That's what happened. We have exceptions. Here are some more exceptions. And they are key questions. Essay questions. We already said first ionization energy is always lower than the second one and the third one. But this is the type of question you will have. I need for you to look at the first ionization energy of sodium. Okay? Look at the second one, higher. The third one, higher. But look at this. Ionization energy, let me reset because it's not what I should circle. Okay? 495, the second one, 4000. Look at magnesium. Magnesium is higher because as you move from left to right, ionization energy increases. But look at the second ionization energy for both. Look at the second ionization for sodium. Look at the second ionization energy for magnesium. Key question, why is it that the second ionization of sodium is much, much higher than the second ionization energy of magnesium? This is what you use. Electron configuration, orbital notation. So if I write the electron configuration for the valence electron for sodium, I have 1s2, the 2s2. You know what? Let me write the whole thing. It's not that long. 1s2, 2s2, 2p6, 3s1, 3s1. Let me write it for magnesium. 1s2, 2s2, 2p6, 3s2, 3s2. First ionization energy of sodium. I'm removing this one. Okay, I'm removing this one. Easy. 3s1, I remove it. First ionization energy of magnesium, I am moving one of those. So I would have 3s1 left. Okay, I remove one. It is higher than, okay. Now, the second ionization energy of sodium, I'm removing it from 1s2, 2s2 to p6, which is number one, it is the second level now. Number two, it is a full energy level. I'm removing it from core electrons. Much, much harder to remove an electrons from the core, the inner core electrons. But the second energy level I'm removing from magnesium would still be in 3s1. Okay? The second electron from sodium is a 2p6 core electrons. Second electron for magnesium is 3, still on the third level, 3s1. Okay, so I need for you to be able to explain all of those big jumps. Not only to be able to explain them, on your test you will have questions where they give you those electron configuration of unknown elements. You need to figure out how many valence electron those elements have. If you see a big jump, that means you are removing that electron from a core level. Core electrons. Okay, let's move on because I don't want to come back to this. Okay, I'm not going to answer all of those questions just to save time. Two questions. Why does the energy increases as you increase the number of electrons we move from the atom? Okay, I'm not going to answer those. Let me just show you, and then you can stop it and try to answer them yourself. Okay, electronegativity is the ability of an atom in a molecule, meaning it's participating in a bond. Electronegativity is really for the bonding unit because those electrons are shared electrons. Okay, to attract shared electrons to itself. Okay, so the trend is increases from left to right and increases from bottom to top. So remember from last year, fluorine is the most electronegative atom. So this is the trend, electronegativity. The good news is you will have more questions in atomic radii and ionization energy than electronegativity and electron affinity. You just need to know the general trend, but you don't worry too much about the explanation because we have so many exceptions. All right? Okay, so I am not going to stay here. You pause the video and try to answer those questions. Those are the exceptions. First, ionization energy because of electron-electron repulsion. So take as an example AS and SE. AS and SE, repulsion, repulsion. First, ionization energy because of screening. When you say screening is when you are going down a group, that means the core electrons will screen those valence electrons. They will protect them. They will, what is the other word? They will those valence electrons outside, the core electrons, are screening them from the force of the nucleus. Use screening, or the other word I was looking for is shielding. Use screening or shielding when you go down a group. Use effective nuclear charge across a period. Now, what happened with photoelectron spectroscopy? You have an activity. This is what happened. It is when you use an X-ray photons, that's mean with large enough energy to lock out electrons from the atom. Okay, you use that high energy photon to remove electrons, not only the valence electrons, but even the most tightly held electrons from the atom. So, what do they really measure from the photoelectron spectroscopy? I promise you will have questions on that. They really measure the kinetic energy. That's mean after you hit that substance, you measure the speed at which those electrons are moving when they leave, when they get emitted. So, but since we don't really need the kinetic energy, what we need is ionization energy. How do you find the ionization energy? Is the energy of the photon minus the kinetic energy will give you the ionization energy. That's how they find the ionization energy from the table. So on your test, you will have questions giving a graph like that to figure out exactly how many electrons that atom has, because the peak, the height, will give you the number of electrons, and the energy, the closer it is from the nucleus, the larger will be the energy to remove it. Okay, let me quickly say before I stop, because this is important. Metals, most metals, hydrides, metal oxides, metal nitrides are basic. Okay, let me repeat, you will have those also. Most metal hydrides, metal oxide, metal nitrides are basic. Most non-metal oxides are acidic. They will react with water to produce acid. It's like nitrogen oxide or sulfur oxide. They will react with water in the atmosphere to produce acid rain. Okay, the NOx, nitrogen oxide, SOx, sulfur oxide, those react with water to produce acid rain. Hydrogen is explosive in the presence of oxygen in the air. You are going to do a lab next week, synthesis of alum. You will be produce some gases, hydrogen gas. You have to make sure there is no flame around, because the hydrogen is explosive in the presence of oxygen from the air. Okay, alkali metals react with water to produce hydrogen gas. All alkali metals react with most metals. The good things about the video, you can pause it right now and then take note, but I have to move on. You can always pause. Alkaline earth metal, calcium, and the elements below it react with liquid water. Magnesium does not react with liquid water, but react with steam. Magnesium and calcium form oxides. Barium forms a peroxide. All alkaline earth metals react with non-metals. And the last page, what are allotropes? Allotropes, the same element in the same state with different structures, different properties. Allotropes are different forms of the same element. Different bonding arrangements between atoms result in different structures with different chemical and physical properties. It's like you have graphite and you have diamond. Okay, they are allotropes, same element, same state, but different properties, different arrangement. For example, you have oxygen, you have ozone, same state, same element, different structures, different properties. Thank you very much for your patience. We are done with the unit. It just means your labs are coming up, your free responses are coming up, and the unit test is right around the corner. Enjoy your day. Bye.